All right, well, it's time to do some practice with rules of differentiation. These are, in some sense, some of the most important practice times that we have because we really want to get these rules down. Our end goal is not to learn all these rules of differentiation. It's to use the rules of differentiation to start answering interesting questions. So do as much practice as you can. We're really just scratching the surface. Go out, make some new functions. I dare say, open a calculus textbook and just start taking derivatives of those functions until you are completely confident in your ability to apply the rules. And the better you get, it's going to make you enjoy the rest of calculus. If you don't get the rules down, the calculus is going to seem really weird and doesn't make any sense. But once the rules become second nature, it's going to be so beautiful. All right, so practice. And make use of that frequent pause button. Try to do everything that you can by yourself before seeing the solutions. You should really think of the solutions as just a way to check to make sure that you're understanding what's going on. All right, well, let's get going. So, our first problem. Find the derivative of x to 2/3 e to the x. Now, one of the things you want to start doing is developing what rules are in play here. Now, there's a couple of things we spot. First off, we see x to 2/3, which means we need to know the rule for x to power. We see e to the x, which means we need to know the rule for the e to the x. And the other thing that we see is hey, these are being multiplied together. In other words, there's a product going on. So we say, okay, so we need to employ the product rule. So what does the product rule say? Well, if I'm taking the derivative of x to 2/3 e to the x, the way I like to think of it is everybody gets a turn. And we'll get into that in another example later on. But everybody gets a turn, right? So I'm going to say the derivative of x to 2/3, what is that? It's 2/3, because the 2/3 comes down, x to the 2/3 minus 1, which is negative 1/3. Then this function stays as is, e to the x. Good, done. Plus, now this function by itself, so see what's the derivative of the first times the second plus the first times the derivative of the second, and e to the x. What an interesting function. The derivative of e to the x is e to the x. It's kind of amazing. It's this beautiful property which makes it an important function, especially when you get into topics like differential equations. They love e to the x in differential equations. They're like, wow, this gets an e to the x, that gets an e to the x, all these things get e to the x. It's really cool. It's really cool. All right. Is that the answer? Absolutely. This is it. So we're done. Woohoo! Now, let's take this second and say, what are some things we can do? I want to pause before I take a second. Wow, there's a lot of pausing. I'm pausing my pause. One of the things that people sometimes get thrown off by is the fact that e to the x, the derivative of e to the x is e to the x. They're like, oh, wait, you just wrote e to the x twice, but really, this was the function e to the x, and here, this was the derivative of the function. So we did take derivatives. So you want to make sure you're keeping in mind, yeah, there were derivatives happening when there's e to the x. You don't want to just be casual about it. You want to be like, this was where I took a derivative, this was where I didn't take a derivative, and keep track of these things. Now, the other thing I want to do is a little bit of practice in saying we should get comfortable in simplifying these types of expressions. So let's talk about things we can do, just some really basic things. So oftentimes when you want to simplify, a big theme that you'll see is let's take the common stuff out. So what do these things have in common? They both have e to the x. Okay, that's common. Let's take it out. What else do they have in common? Well, they both have x to powers. So we see like there's an x to the 2/3, there's an x to the minus 1/3. All right. So we want to plot x to a power. Now the question, and I'm going to ask you this, what power do we pull out? What's the right power? Do we pull out negative 1/3 or do we pull out 2/3? And why is it negative 1/3? And that's the right answer, by the way. It is negative 1/3. Why would we pull out negative 1/3? Well, the rule is when you're pulling out a power of x, you always pull out the smaller power. And so negative 1/3 and 2/3, negative 1/3 is smaller. That comes out. Okay, that's the rule. That's why we do it. So in fact, look, we got both the x to the negative 1/3 and the e to the x. So what's here is 2/3 plus, we got the e to the x. Now, here's the part that people are like, but let's be careful here. What goes here? So it should be x to some power, but x to what power? Well, one way to think about it is you could say, whatever's here, when I multiply x to negative 1/3 has to leave me with x to 2/3. And if you think about that logic, you'll end up with, oh, it should be x. Now, another way to do it is to say, when I'm pulling something out, I have to subtract from the exponent what I pulled out. So I pulled out negative 1/3, so I'd have to take 2/3, subtract a negative 1/3. Well, that's 2/3 plus 1/3, which is x to the 1. Now, this is another answer. They're both right. It just is a matter of, do you want to simplify or you do not want to simplify? Generally speaking, we don't really care too much about simplification as a rule of thumb. There will be cases when you do want to simplify. Really what I like to say is, are you going to do something else with it? If you're going to keep doing something with it, there's additional steps later on. You should simplify as you go along. If you're at this is the final stage, there's not much use in simplifying, and I usually leave it alone. So that's sort of my rule of thumb. As a side note, please follow instructions. So if you're taking an exam, make sure you do what the exam tells you to do. All right, now let's do another one. Okay, so let's find the derivative of e to the power 2x. Now, we're going to be able to do this one really quickly in the future. But for now, we're like, oh, well, what is e to the power 2x? What is that derivative? So let's think about how we do it now. Well, one way to do e to the 2x is it's the same as e to the x times e to the x. And you can see that because when you have the multiplication, e to something, you add the exponents. So x plus x is 2x. Okay, so we can say what? The derivative of e to the 2x. All right, so I'm just following it along. That's the derivative of e to the x times e to the x. Now, what rule do we need? We need the product rule because it's a product of two functions. So be careful here. Let's say it out loud what's happening. We're going to take the derivative of the first, e to the x, times the second, e to the x, plus the first, e to the x, times the derivative of the second, e to the x. So it looks like I wrote down a lot of e to the x's, but keep in mind, sometimes e to the x is the function, sometimes it's the derivative, and you want to be careful. Be patient, be methodical. Now, we know that when you have these together, you get e to the 2x, and this would also be e to the 2x, and so we have two of them. So that makes 2e to the 2x. Oh, okay, well that's kind of nice. So when we took the derivative of e to the x, we got e to the x. When it's the derivative of e to the power 2x, we got a 2e to the 2x. That's interesting. That's interesting. You know, I wonder if there's a pattern here. I think that there might be something going on. If we could have a way to take these derivatives simply, you could really say that that would be a real game changer. Well, if only such a rule existed. We'll see. We'll see. All right, next problem. Find the derivative of f of x, which is x squared plus 2x plus 2 times e to the negative x. And it says, hey, as a first step, you should find the derivative of e to the minus x. Okay, now I should say, you can avoid finding the derivative of e to the minus x. You could say, hey, I could think of it in the following way. This is really x squared plus 2x plus 2 over e to the x. And then you could say, do quotient rule. So why does it say, find the derivative of e to the negative x? Well, probably what they're trying to get at is, don't think of this as a quotient, think of it as a product. So it's x squared plus 2x plus 2 times e to the negative x. So we're going to be applying the product rule, not the quotient rule. Okay, so let's do our first step. The derivative of e to the minus x. Okay, well, now that's the same as the derivative of 1 over e to the x. Because when I have a negative exponent, it means I put it downstairs. All right, well, what do we have? This is the reciprocal rule. Do you remember that? 1 over something. So the reciprocal rule says you take the negative of what's downstairs. Well, I should say the derivative of what's downstairs. So the derivative of what's downstairs is e to the x divided by the downstairs function squared. Okay? So the top is the derivative, the bottom is the function being squared. It's hard to keep in track, right? Because of e to the x can be tricky like that. Okay, so what do we end up with? We have negative e to the x over e to the 2x. Well, I can now subtract x, subtract 2x. I get negative e to the negative x. Ooh, hey, we just did a problem just a second ago when we said the derivative of e to the 2x. The 2 came out in front. And now there's this minus sign was here, and the minus sign comes out in front. There's got to be something there. I tell you, if we just could understand it better, it would be a real game changer. Well, I'm sure we'll get there eventually. All right, well, we're not done yet, right? We've only found the derivative of e to the minus x, but now we're in good shape because, notice, it's a polynomial, and we like polynomials. Polynomials are easy to work with because they're powers of x's, and we know how to work with powers of x's. So the derivative of x squared plus 2x plus 2 e to the minus x. So I come to the first term. I see that there's a lot of things being added, which means I take the derivative of each piece and add it up. Derivative of x squared is 2x. Derivative of 2x is 2. Derivative of 2 is 0. Derivative of a constant is always 0. So the derivative of the first times the second plus the first, x squared plus 2x plus 2, times the derivative of the second. So the derivative of e to the minus x, that's what we did up here, minus e to the minus x. Now, justifiably, we're done. But I suspect there's something going on here because I see similar things here. They both have e to the minus x's. They both have other pieces that are similar. So let's clean it up. Let's factor out e to the minus x and see what's left. So here we'll have 2x plus 2. On the end, don't forget that minus sign. See, sometimes the minus is up here, but this one is in the back. So that minus sign didn't get factored out. So it's going to distribute through. So minus x squared, minus 2x, minus 2. And what do you notice? You got a plus 2x and a minus 2x, a plus 2 and a minus 2. Almost as if they had planned to do that, because they had planned to do that. So what do we get? Well, we're left with minus x squared e to the minus x. So this is kind of fun. You know, this is an example where you might have a complicated expression for a function whose derivative is very simple. That can happen. Of course, it can also happen that you have a simple function whose derivative gets a little bit more complicated. So, well, you follow the rules. You follow the rules. All right. Our next problem. Okay, good. Find the derivative of 5x to the 12th minus x cubed plus square root of x plus 3 over x plus 17 e to the x plus pi squared plus e to the 100. All right. Now, let's work through this and let's make some notes. Now, the first thing to note is it's lots of things being added and subtracted. So one of our first rules says when you have lots of things being added and subtracted, you get to do every single little individual piece. So in other words, that's because we have that linear. We break up over addition. This is cool. So instead of thinking of it as one big problem, we can think of it as 6 or 7 little tiny problems. So you might say, well, that sounds like a lot more problems, but each one is very straightforward. Now, the first thing we should do is make this written in a more calculus-y type way. Now, you might say, what do you mean by that? Well, this part right here in particular, the square root symbol, it's a cool symbol, and you're so used to working in algebra, but when it comes to calculus, it's not a very convenient symbol. So when I talk about rewriting in a more calculus-friendly way, what I want to do is replace that square root by something where I can write it as x to a power. So it'll become x to the power 1/2. Now the other thing I want to do is this 3 over x. 3 over x, I'll write it as 3, and the 1 over x becomes x to the minus 1. So this is now more calculus friendly. In other words, what's happened is I have made it so that I can fit my rules to the situation. We want to make them compatible with our rules. So now we go through term by term and we think about what's going to happen. So on the first term, derivative of 5x to the 12th. Well, 5 is a constant. Then you think about the derivative of x to the 12th. The 12 comes down, and then you subtract 1. So 12 subtract 1 is 11. No surprise there. Minus is really just plus with an extra little bit. It's a pessimistic plus, right? That's exactly what a minus is. Derivative of x cubed. 3 comes down, subtract 1 from the power. 2. Derivative of x to the half. So the next term, half comes down. Subtract 1 from a half, minus a half. Okay, next term. 3 is a constant. You just write it down. So x to the minus 1. Bring the minus 1 down. X to the minus 1 minus 1, minus 2. 17, a constant. All right, e to the x, derivative of that, e to the x. Okay, now we get to the fun ones, where it's like, are you paying attention? Because I'll tell you, I'll write down some answers that I see and think about why they're wrong. Pi squared. Oh, I know how to do like that. That should be 2 pi, right? Right? Wrong. It's not 2 pi. Why is it not 2 pi? Well, what's true about pi squared? Well, first off, pi should be round, not square. But actually, what's really wrong here is that pi is a constant. So pi squared, it's a constant. And the derivative of a constant is 0, so it goes away. Okay, well that was the pi squared one. Now the derivative of e to the 100. And again, what do I see written down sometimes? People write, oh, that's e to the 100, right? Right? Wrong. It's not e to the 100. What's wrong here? Well, it's e to something. Okay, well if it's e to something, shouldn't that be the derivative of e to the x is e to the x? Shouldn't the derivative of e to the 100 be e to the 100? No. Because what's true about e to the 100? E to the 100 is a constant. It's a strange looking constant, but it's still a constant. So if you take the derivative of a constant, you get 0. Good. Gone. All right. So what do we get? Well, we get 60 x to the 11 minus 3x squared plus 1/2 x to the minus a half minus 3. And if you write, some people like this as 1 over x squared. You can do it if you like. I don't know. Plus 17 e to the x. You could have also written this as a 1 over root x. It just depends what you're in the mood for. But there you go. There's our derivative. Good. Break things up. Smaller pieces. Make it a little bit more easy to digest. All right. Here we go. Find the tangent line at x equals 1 to the curve y equals x cubed plus root x minus 2 over e to the x. So there's this curve. I don't know what it looks like. It looks like something. I don't know. But I'm after a tangent line. So implicitly it's saying, hey, how is this function, this curve, what does it look like locally near 1? That's what I'm really going to answer by finding that tangent line. Well, so we think about what we're doing. Now, of course, there's the key word here, which is line. Now, why do I say it's a key word? It means I need to find a line. My answer has to be a line. And whenever I see that I'm looking for a line, I say, hey, if I'm looking for a line, there's 2 pieces of information I need to discover. So I need to figure out a point on the line, and I need to figure out the slope of my line. Those are my two pieces of information. Now the point's usually the easier one, because I know the x-coordinate. Okay, so 1, comma. How do I get the y-coordinate? Well, we plug it in. So let's see. We'd have 1 cubed, which is 1, plus the square root of 1. Well, that's 1, minus 2 over e times e to the 1. All right. Oh, well, e to the 1 is e. The e's cancel. 1 plus 1 minus 2, that would become 0. So there's our point, 1, comma 0. That's actually pretty easy. All right, how do we get our slope? Well, to get our slope, we need to know the derivative at that point. So what we'll do is we'll find the derivative, and then once we have that, we'll evaluate. So since we have it as y equals, a nice way to write the derivative is to say y prime. Some people also write it as dy dx. So y prime would be what? Well, we think about our function. Ooh, there's a square root of x, so let's take a second and rewrite that as x to the 1/2 so that we can get it into our friendly calculus mode. So derivative of x cubed, 3x squared. Derivative of x to the 1/2. 1/2 x to the minus 1/2. This 2 over e is a constant, so minus 2 over e, that's just a constant, times the derivative of e to the x, and the derivative of e to the x is e to the x. Right. Good. Good. Now, plug in 1. There's a couple ways to write that. You just say, y prime of 1. Some people will write that. Or you could say y prime at x equals 1. Or you could just plug in, do the evaluation, and say, now evaluate at 1. So either way, what are we getting? Well, we're getting 3 times 1. 1 to any power is 1. 3 plus 1/2 times 1, which is 1/2, minus 2 over e times e to the 1, which is e. Well, the e's cancel. So what do we have? We have 3 plus 1/2 minus 2. So that becomes what? Well, 3 minus 2 is easy. That's 1. 1 plus 1/2 is 1.5, which we often write as 3/2. So keep in mind, this right here, this piece, let me change my colors just to make this comment here. This right here, this is the derivative function. This is not the slope yet. So we don't get the slope until we evaluate. So to find the slope, we need to evaluate. This is an important thing to keep in mind. There's a lot of students that make that mistake, and they say, oh, so now I took the derivative, so that would be my slope. No, this is not your slope, because your slope should be a number. It should never be a function. You have to evaluate. Then you have your slope. Okay, so our slope, well, that's 3/2. Good. Now we're ready to go. We have our point, our slope, y minus our y-coordinate, 0, is equal to our slope, 3/2, x minus our x-coordinate, 1. Or we can say that y equals 3/2 x minus 3/2. And there you go. There you go. Beautiful. Nice. Beautiful, nice answer. We like beautiful, nice answers. All right. Now, our next problem. We talked about this when we went through and talked about derivatives. Here we go. Time to flex all our rules, our rule abilities, right? So this is a quotient rule. There's all sorts of things involved. So we're just going to go through and just be patient and be methodical. So here we go. We start by saying it's a quotient rule. That's the outermost layer of this onion. And really, a lot of times when you're taking derivatives, you're going to have layers upon layers upon layers of rules. So that taking derivatives is a lot like working with onions. Namely, there's lots of layers and there might be some tears involved. All right. So when we're taking this, we say, all right, the bottom times the root of the top. Now, of course, I'm going to keep doing the same thing. Square root of x becomes x to the 1/2 plus x squared. Whoop, forgot my derivative symbol in front. So I I always like to rewrite the square root as something to a power. Make it more calculus friendly. So we're going to take the bottom, 3x cubed plus x e to the x, times root of the top, 1/2 x to the minus 1/2 plus 2x, right? Root of x 1/2, 1/2 x minus 1/2, root of x squared, 2x, and we add them together. Subtract. So bottom times root of the top minus the top, x to 1/2 plus x squared times root of the bottom. Well, root of the bottom. Go term by term. Root of 3x cubed, well, the 3 times 3x squared. So that'll be 9x squared. Derivative of x e to the x. Okay, product rule. So derivative of x, so first off we're going to add that. Derivative of x is 1 times e to the x plus x times the derivative of e to the x, which is e to the x. Okay, good, right? So bottom times the root of the top minus the top times the root of the bottom. We had a little bit of a product rule in there. All that divided by the bottom squared. All right. Now, what comes next? The answer is we box it. We're done. Now you could say, couldn't you expand that? Couldn't you multiply it out? And the answer is, you could, but that sounds like work. And also, it sounds like we're setting ourselves up for potential missed points if we were taking an exam or doing homework. Because oftentimes what happens is we can do the calculus, but it's the algebra. I know it's crazy. It's like, I know algebra. I know you know it. But do you know it on like a deep personal level? Are you like algebra on a first name basis? Do you say, hey Al, what's up? Maybe. But oftentimes, it's really easy to make mistakes. And so, if you don't have to do anything else to it, and in this case we don't, this is a great point to say, all right, I'm pretty satisfied. I think I'll stop right there with that problem and go on to the next one. All right, so on to the next one. All right, our last one for this round. Okay. So suppose we know some information. We have a function f, and we're told the following. Namely, f of 1 equals 2, f prime of 1 equals negative 3, g of 1 equals 1, g prime of 1 equals 4. And that's about all we're going to know about f and g. So we actually don't know what f and g are. But we also are told that h of x is e to the x times f of x plus 2x squared g of x, and we're asked to find h of 1 and h prime of 1. Okay, so first off, can we do it? In other words, even though we don't know what f and g are we going to be able to answer this question? Now, I think pretty much every question that gets asked during the class, we're probably going to be able to answer. So it should be yes. And here, it is a yes. So what are we being tested on? What we're being tested on here is really, can you apply the rules and just follow what it says? So let's just follow the rules. So, first off, let's find h of 1. So what that means is we're going to plug 1 in. So h of 1 would be, if I follow the rule, it's e to the 1 times f of 1 plus 2 times 1 squared times g of 1. So what I've done is I took this expression, and everywhere where I saw an x, I put a 1. That seems to be a pretty reasonable thing to do. Now I say, what do I know? Well, I know a couple of things. I know what f of 1 is, and I know what g of 1 is. And you might say, how? Because I was told that earlier. Okay, so let's put those in. So we have e times f of 1, and f of 1 is 2. So that would be 2e plus 2 times 1 times g of 1. Well, 2 times 1 times 1. So plus 2. And there we go. There's our h of 1. Woohoo! We got it. We got it. All right. Now, how do you find h prime of 1? Well, to find h prime of 1, we're going to do a two-step process. So the first step is we're going to find what is h prime of x symbolically. After we found h prime of x, then we're going to evaluate 1. Now notice you got to take the derivative before you evaluate. So we can't say, hey, now that I found h prime of 1, let me take that derivative. Why would that fail miserably? Well, if you think about it, when I find h of 1, what have I found? I found a number. And if I take the derivative of a number, I'm going to get 0. So you can't take the derivative after you evaluate. You first got to take the derivative, and then you have to evaluate. Okay, so back to where we were. All right, so h prime of x, product rule. So we're going to take the derivative of the first. Derivative of e to the x is e to the x times the second. Now, I will say sometimes people swap the order. It doesn't matter. As long as you keep it consistent and you get the right answer, we're happy with it. Okay, so the derivative of e to the x times the function plus just the function e to the x times the derivative of f. Now, what is the derivative of f? The answer is the derivative of f is the derivative of f. So we just write down what the notation is. It's f prime of x. Okay, so that's sort of the first part. Plus, okay, derivative of 2x squared. Well, it's 2 times the derivative of x squared, which is 2x. So it becomes 4x. I like to think of it as the 2 comes down, 2 times 2 makes 4. Then times the function. We leave that alone for that part. Add to that 2x squared, no derivative, times the derivative of g, which is g prime of x. Okay, so there's h prime of x. Now we'll do the same thing where we plug in 1. So we have that h prime of 1 is e to the 1 times f of 1 plus e to the 1 times f prime of 1 plus 4 times 1 times g of 1 plus 2 times 1 squared times g prime of 1. Okay, now we already know that we have f of 1 and g of 1. But of course, no surprise, we also know f prime of 1 and g prime of 1. Now, how do we know them? Well, because they were told to us way, way up here. So we know them. All right, so what we're going to do is we're going to plug in what we know. So we're going to get e times 2. So because f of 1 is 2, so 2e plus e times f prime of 1. So f prime of 1 is negative 3. So that'll be minus 3e plus g of 1 is 1. So 4 times 1 times 1, so plus 4. And g prime of 1 is 4. So we're going to get 2 times 1 times 4, which is 8. So 2e subtract 3e would be a negative e. 4 plus 8 is 12. So 12 subtract e. There we go. That's the answer. Ah, good practice. Of course, keep doing practice. These rules are so important. If you can make these rules just so natural and just carry them out, it makes calculus so much more fun. And if you can't get the rules down, the rest of calculus is going to be very mysterious. So practice, practice, practice. All right, keep going.